right. So hey everyone. So this talk is more regarding like Web 2 developers or traditional developers coming to Web 3. So if you're already like a smart contract expert, maybe use this time to like do your hackathon. So a bit about myself. I'm Shayan Iskandari. I'm a CTO at Ether Capital, which is a publicly traded company. Previously, I worked with Consensus Diligence as smart contract security auditor for 3 years, and before that, I was working on Bitcoin ATMs and software. This is pre-Ethereum. So, and on this kind of parallel life, I'm doing my PhD on blockchain and new crime and the evolution of crime. And also, I did some usability studies on key management and on like Bitcoin usability. So just getting into this, like we're just talking about like Ethereum, smart contracts being a new paradigm of software development. And what I mean by that is there is a lot of like ideas in your mind that you have to change when you want to work on a smart contract. And this is basically like one of the examples, one of the experiences I went through when I started working on smart contracts. And the idea was we wanted a smart contract to do an API call. And basically, I told my boss back then that it's going to take me 2 days to figure out how Solidity works and do this. And my idea was like, I was working Python, so it's 2 lines of code, just call like a URL. And in my mind, something like this should have worked as the call a URL to get some data on the smart contract. Anyone here, do you know like why this doesn't work? Like, why can't you call just API with a smart contract? There are stickers there as a prize if you want. Any idea? No? So just you have to like see mentally like where this code is being executed. Like when on Python, you have this computer sitting on internet, calling this API, getting the data, writing it wherever that you want to write it. But for Solidity and a smart contract, the code is not executed in the same place, same time. All the nodes, Ethereum nodes, are running this code, and they have to come up with a conclusion. So you can see blockchain or Ethereum as this closed system that is online. So it doesn't have access to like outside information. So you can't really call an API. And all the nodes should get into the same state at the end. So when you're calling, let's say, a price of oil, within seconds, the price might change, and like all these nodes would have different results. So you can't really come up with the conclusion that this is the consensus on the latest data that is going to be saved on this smart contract. And for this solution, like Oracles is basically the solution. And I was so naive to thinking like I can do this in 2 days. And Oracles are still today is kind of like a challenging problem to solve. So I want to go through like a few other examples and let's work together. This is more interactive workshop, so let's try to like be more engaged. So let's say we want to have a smart contract that is password protected. So basically, you can save the password on a smart contract and ask for the user for the password to unlock the vault. Anything wrong with this idea? Like, can you do this on a smart contract? Can you save the password and ask the user for the password? So much excitement in this room. So I'm just going to go through this. So you can't, because all the data on blockchain is public. You can't even, like, even though that variable is set as private, you can't really have any private information on a smart contract. So if you save the password on a smart contract, it is visible to anyone that has access to that blockchain and everyone in the world. So in the traditional sense, the traditional security, they say instead of saving the password on the on your database, save the hash of the password on a database. So anyone having access to the database, they can't really know the password. And on Ethereum, we have this function called getcheck or SHA-3 that you can save the hash of the password. So let's say if you use this. So we save the hash of the password, and we ask for the user for the password, hash it, check with the hash that is saved, and see if it matches. So this should solve that problem that we had earlier, right? Like that the password is not saved on blockchain. Anything wrong with this? Yeah, good. So there are stickers there as a reward if you want to get that. I'll give you some after. So in order to understand what this problem means, And first of all, why this could be an issue is like, let's say that Vault is holding 100 Ethereum, and anyone having access to that unlock can get 100 ETH out. So this is where it gets more tricky. So now I want to get into why this is an issue and what our friend mentioned. So let's get into the metrics. Oh, Ethereum. Yeah, let's get into Ethereum. It is a decentralized public permissionless blockchain that technically it's different from online and cloud services. So going through quickly into how Ethereum or decentralized networks work. Basically, on the cloud storage or client server, you see a request to the server and a response. But on blockchain, basically, you create a transaction locally, you broadcast it to the decentralized network. Everyone else are doing also the same. Recent transactions are kept in this part of every node called mempool. And miners basically come, they look at their mempool, they choose some transactions, and they put it in a block. And they use the hash of the previous block, so it's all a block, a chain of block, or blockchain. But in this case, so miner has control over how the transactions are ordered in that block. So they can basically change the order. But also consider what the incentive model of Ethereum is. Blocks are scarce. The block size is limited because of computation, storage, network, and other reasons. Just to know we're on the same page, gas basically is a payment for the computation, and the main point here is the gas price, which is the price you pay per ether, and that defines how exciting or how more profitable that transaction is for miners. EIP 1559 changed a bunch of things here, like the base fee and others, but the whole idea is the same. The more you pay as a gas price, the more profitable it is for the miners to mine your transaction. So the idea here is the miners or anyone sending higher gas price, or now with the whole recent trend of MEV or flashbots, which some of you may know, they can change the order of transactions within a block. So you send a transaction, someone else using one of these methods can change the order of the transactions in a block. So what does that mean here? Another kind of side note, this whole issue is called front running, and the idea comes from a stock market or traditional sense that basically someone has some benefit of some market information, or let's say someone goes to their broker and asks for $1 million of a share. Someone else is hearing this. They run in front of the broker and buys the stock and profit from this price change. And it's usually because of the privileged position along the transmission of the data. And in the blockchain, it's a bit different because everyone running a full node, they have access to all this privileged information. Everyone see the transaction coming in the network, but not yet verified. So miners are in the more privileged positions, but also, as I said, MEV or maximum extractable value or flashbots basically change this whole game, and anyone can change the transaction order by paying some of the portion profit to the miners. If you're interested in this subject, there's a paper I did 2 years ago on transparent dishonesty or front-running attacks on blockchain. It's an interesting paper because where I was writing front-running CryptoKitties breeding function, it was a weird feeling to have, why am I writing on an official paper on breeding CryptoKitties? I don't have my laptop. This is not my laptop, so I can't really show you the live demo. But this helps on idea of how a blockchain and mempool works. I'm just kind of jump in the front because this is really cool. If you have a laptop, go on these two websites on the corner, the ethviewer.live and txstreet.com. These are really cool visualization of how blockchain works in a real time. Just leave it for a few seconds. All right. So basically, the general idea is the front-running blockchain is these blocks are coming, but someone's I want to insert my transaction here, and they can just insert their transaction in the middle of every other blockchain, any other block. So coming back to our example, this transaction, let's say someone saves the password as a hash on the vault, and then someone else is calling unlock with the real password to get the money out. So anyone else seeing this transaction, they can pay more gas and front run the original transaction with the right password and get the money out. So that's one of the issues. Yeah, that's like what I'm saying, like we can pay higher gas price. So the solution to this is something called commitment schemes or commit and reveal. And the general idea is you hash everything, all the information that you have, you send the transaction with that hash, so you basically save your spot in the line, and then you send another transaction revealing all the data, so a smart contract can hash it, see your location in the line, and then execute that. So a lot of, basically it's a solution to front-running attacks, a lot of blind auctions or gambling games. You can do all these kind of things because you commit to the value before you reveal the value. I want to use like a real-life code auditing example, talking a bit about code auditing and security while showing what all these means and bring them together. So as I said, like I spent 3 years of my life like doing smart contract auditing. It was really interesting because I realized the manual code review and in-depth understanding of the system and documentation is really needed, and you can't really have like security tools do everything. There are some of the issues that you cannot really find using the automated tools. And so in this example, it's really good that Austin was talking about the ENS, because this is one of the examples. So ENS, Ethereum Name Service, or naming service, is basically the human readable names to identify Ethereum addresses. So a classic example on DNS is google.com. That is like an IP address. You don't have to memorize the IP address. Similarly, .eth, like, I don't think google.eth is like directed to that, but it's like you can use instead of like Ethereum addresses. And they use this on-chain transaction. So they use this blind auction on-chain to like get the new domains. But in 2019, they switched to instant domain purchase with a rent-based model, which you now know as ENS, how you interact with ENS and you get the domains. It's called ETH registrar, which basically they hold funds in a smart contract and require the commit reveal to prevent front-running. Because if you want to register a domain, you send a transaction, you don't want anyone else to jump in front of you and get your domain. So you send the hash, and then you reveal what domain you want to get. So I don't have the laptop here, but like, if you're working on a smart contract auditing or any other thing, I really suggest using VS Code with Solidity and Solidity Visual Developer extensions, because you see the colors and everything, and you can jump into the code, do some of the checks and security checks within the code while you're writing it. It's a really interesting one. So I'm just gonna like go through the abstract idea. If you also wanna like read this code, so that link bit.ly /ENS registrar goes to a pre-audit or January 2019 ENS code. I'm just going to jump on like the actual details, like abstract away the code. So to prevent front-running, ETH registrar controller requires a commit reveal process, as I mentioned. And the way it works is it generates a commitment hash from the name you want to register and with the secret value that you come up with. Because if you don't have it, anyone can start generating hash with different names and kind of like see what name you're registering. And then you register a commitment to the controller. You wait at least a minute, but not longer than 24 hours. And you register the name with the secret and everything that you need. So basically, these are the functions that it's calling. Like make commitment with the commitment. It commits the transaction, commit value, and it registers name, owner, duration, and the secret. So to remove all the words from there, basically the first transaction is make commitment with name and secret. You commit to that value, and you register name, owner, duration, and secret using base register. There's something wrong here that doesn't prevent that. Oh, 5 minutes. Can you spot any issues with this commit and reveal? So the first commitment is with the name and secret. You commit to that, and you register using name, owner, and secret. I have $100 million, trillion Zimbabwe dollar here for the prize.
Is the person minting the domain name, is that hashed in the secret, or how's that tied back to that person?
So yeah, you're right path. So the commitment doesn't include any of the owner details. So the example here, if someone, because you're right path, let me just give you this. So the main issue, like, let's go through the attack scenarios that makes it more visible. So it is vulnerable to front running. Why? because commitment is not tied to the specific owner. So how does the attack scenario work here? Let's say Alice wants to register my domain. I actually changed these in the slides, so it's much more visible. Anyways, so Alice wants to commit to the domain. She sends commit my domain. 10 minutes later, Alice sends a transaction to register my domain, Alice, like her own address, and secret. But then Eve sees this transaction in a mempool, and she sends a transaction with my domain, Eve, and secret, because the owner, Alice, was not part of the initial commitment. So anyone can just swap their own address with that, and then basically register Alice's address for themselves, and then probably sell with profit. So here, exactly, the issue was commitment was not part of the owner in addition to the names, and it should be. Like, you always make sure every variable in the system that you care about is part of the commitment phase. But also, like, consider, like, this is ENS code. This is like really good quality code, but still, like, these issues exist, and you can't really find this bug with automated tools because like, it's a more logical security issue. And if you're interested in these kind of vulnerabilities, there's a lot of papers and resources. There's a specific paper which did a pretty interesting survey on Ethereum security, system securities. I'll send the slides later on Twitter, so you can like find them there with all the links. There are so many other tools that you can use to either read more or learn about like some code analysis, or mainly how to write more tests. And also fuzzing is the new way of doing it. The last three also are challenges, the security challenges that are like kind of capture the flag. It's really fun to like start hacking smart contracts and learning how JavaScript, Web3, and Solidity works. So I think I'm done with this, and also about the time. So if you want to know more, feel free to reach out, and I'll be happy to help you out with that. Thank you.